These are the notes on periodic trends, CERs. So I'm going to go through just a couple of practice to look at how we could discuss each or write a CER for each of these. You should have a periodic table. Otherwise, you can use the one that I have down here. I do also have my periodic trends that are labeled on here. We should have labeled those in the lab kind of summary notes. And we can use these trends that are labeled to make sure we're talking or that we're making the correct claim. But when we're talking about explaining our claim, we are going to use Coulombic force and the structure of the atom to relate it back to the definitions of each of these. So let's look at our first one. Which element is the most reactive? Oxygen, sulfur, or selenium? So when I'm looking at these, the evidence I need, evidence is going to be information from my periodic table on structure. So as we look at this, so oxygen has valence electrons in energy level. Feel free to abbreviate like I do. When we look at these, oxygen is here. Energy level is the row that it's in, so energy level 2. So oxygen has valence electrons in energy level 2. If you want, you could state the number of valence electrons. Sulfur has valence electrons in energy level 3. And then we've got selenium has valence electrons in energy level 4. And so I could add more evidence in here, but right now what I'm seeing is looking at this, these proximities. All of these are in different energy levels. That's going to be enough for me to make a claim about Coulombic force with that. The other thing though is if I'm looking at reactivity, these are all nonmetals. And so I can state my valence electrons. So oxygen has 6 valence electrons. I could have done that within my evidence statement. I probably should have. Sulfur is going to have 6 valence electrons. And same thing with selenium. It also has 6 valence electrons. So now when I'm looking at this, which of these is the most reactive, we can follow our trend. We've got oxygen, sulfur, selenium. These are all nonmetals, which means if I look at my reactivity of nonmetals down here, which is my red, reactivity is going to increase as we go up. And so this is showing me that oxygen is going to be my most reactive. And so my claim is that oxygen is more reactive than sulfur and selenium. How do I explain that though? I can't just say because it's at the top. I have to talk about what about the structure this means. So when we're talking about reactivity, we need to talk about Coulombic force. We also have to talk about reactivity in thinking about how will my atom become more stable. And because all 3 of these are nonmetals, 6 valence electrons, it's going to be easier for all of them to gain 2 electrons to get to a full octet than to lose 6. So we need to keep that in mind. And so I'm going to just state in my reasoning all 3 elements are nonmetals and want to gain 2 valence electrons to reach a full octet and become stable. So now me thinking of which of these is going to have the capacity to gain those 2 electrons better, I can relate that to Coulombic force. And how am I going to attract those electrons from another atom more easily? Well, it's going to be if I have a strong Coulombic force. So I want to go from here and figure out which one of these is going to have the strongest Coulombic force. And we can talk about that in terms of proximity and nuclear charge. We only have to pay attention to protons in the nucleus if the proximity is the same. Otherwise, we use proximity first. And so which one of these is going to have the strongest Coulombic force? Well, oxygen's valence electrons are in the lowest energy level. So let's discuss that. So oxygen's valence electrons are in the lowest energy level. And that means, what about our proximity? So the valence electrons are closer to the nucleus and experience a stronger Coulombic force. So that's how I know I have a strong Coulombic force. Relating this back to that definition of what do these want to happen, that means it's going to be able to gain or attract those valence electrons more easily. So Coulombic force, meaning it will attract more valence electrons, more electrons, let's say, more easily. And so your wording on that doesn't have to be the exact same. In our reasonings, we kind of want to use comparing words. We have all of our evidence already on, like we have the specific things listed. And so I'm going to use then comparing words in my reasoning with that. I didn't actually have to like say 2 electrons here. I can just say they all want to gain, but then a comparing word. So lowest, closer, stronger, with that. All right, let's do another one. So which element has the lowest ionization energy? With this one, if we're talking about ionization energy, that's what it's asking about. The things that we're going to need to use in our definition, or in our reasoning, is we need to discuss the definition of ionization energy, and then we're going to relate that with Coulombic force using our evidence. So I'm going to go through and get my evidence. So I'm looking at aluminum, silicon, or phosphorus. So aluminum, silicon, phosphorus. And again, looking at those ones, we can look at our trend for ionization energy, which is this gray one down here. As we go to the right, that increases. So I can use those arrows to determine that phosphorus is going to have the greatest ionization energy. But then I need to explain what that means and how my evidence supports that. All right, so I'm going to say all 3 of these have valence electrons in energy level 3. So aluminum, silicon, and phosphorus have valence electrons in energy level 3. With this, though, I can then say, well, what is different if we're thinking of that ionization energy and that Coulombic force? Well, proximity is the same. So Coulombic force is based on proximity and nuclear charge. Well, what charge is in the nucleus? That's going to be our protons. So now let's talk about how many protons they each have. So aluminum has 13 protons. That's our atomic number. Silicon has 14 protons, and phosphorus has 15 protons. Again, those are my atomic numbers. And so now as I'm looking at this, and I can then write down what my claim was over here, which one has the lowest ionization energy. Oh, excuse me, I flipped this when I was up here. So phosphorus is going to have the greatest, which means aluminum is going to have the lowest ionization energy. So I want to make sure I'm actually answering the question. In my claim. So aluminum has the lowest ionization energy. So we need to talk about how does this relate to Coulombic force. Sometimes it's nicest to look at that definition right away. What is that definition of ionization energy? And you can always put that right away, or we can talk about that later on. The definition of ionization energy is how much energy is required to remove an electron. And so when we're thinking about this, if it's going to take the least amount of energy to remove an electron, that means we want to highlight that aluminum has the weaker coulombic force with that. So kind of thinking, how do these two things connect? So for my reasoning, I'm going to be talking about aluminum, what's different. I'm going to say all three elements, actually atoms, have valence electrons in the same energy level. And then I'm going to say aluminum has the least protons. So the weakest nuclear charge, that is just charge in the nucleus. We just focus on the protons for that. Weakest nuclear charge. And then if you have a weak nuclear charge, you're going to have the weaker coulombic force. So now we have talked about coulombic force. So how does weak coulombic force relate to that ionization energy? We can then say, since aluminum's valence electrons experience less coulombic force, it will require less energy to remove its valence electrons with that. So I discussed my coulombic force, comparing that structure based on what I got from the periodic table. And then my definition of ionization energy is in here, connecting coulombic force, less energy to remove valence electrons within my reasoning. All right, if you want, feel free to pause, try the next one on your own. Otherwise, we've got one more to do together. What element has the largest atomic radius? So we're going to have to talk about coulombic force, and we're going to have to use that definition of atomic radius, which is the distance between the nucleus and valence electrons. And the definitions of ionization energy, atomic radius, and electronegatividity, those are on the lab pages that you have. Those were also in the pivot. So make sure you know those. All right, so we're looking at beryllium, calcium, and barium. So we've got beryllium. There's calcium. Oh, beryllium, barium. There we go. And so with this one, now what we can look at is where are those valence electrons. So how can we discuss the size of that atom? I'm going to go through, and because these have valence electrons in different energy levels, that's going to be what determines the size. That proximity is what we're going to discuss first. So going through and writing those out. So beryllium's valence electrons are in energy level 2. Calcium's valence electrons are in energy level 4. And then barium's valence electrons are in energy level 6. So again, using those row numbers. And this is actually the one time when we're not going to need to use coulombic force, because we know that proximity is determined by that energy level. So which element's going to have the largest atomic radius? Which element is going to have its valence electrons farthest from the nucleus? Well, these valence electrons are in the highest energy level. So barium is going to have the largest atomic radius of these three elements, okay? So what is our reasoning? We can state that barium's valence electrons are in the highest energy level and farthest from the nucleus. So that means that, barium has the largest atomic radius. And again, I don't need Coulombic force in when we are specifically talking about atomic radius and we have our valence electrons in those different energy levels. But I am discussing what does it mean to have a large atomic radius. I can't just say they're in the highest energy level. I need to say that the valence electrons are farther from the nucleus, because that is our definition of atomic radius. All right, reach out with any questions, and good luck.